Okay, so this is from the last time. So we had started Compton scattering. Okay, so here is like a brief recap of it. So we talked about this, the classic calculation of energy loss in Compton scattering. We applied conservation of momentum and conservation of energy and obtained this relation for the energy of the photon, which is scattered by angle theta in electron rest frame. So electron is at rest, so it can only gain energy, it cannot lose energy. So the photon loses energy and the electron gains energy, and this is the expression for the energy after scattering. So then we also talked about this properties of Compton scattering, that is, the Compton you are in the Thomson limit if your wavelength is much less than this Compton wavelength, and you're in, it's elastic scattering. So that's the first effect. The second is this Klein-Nishina suppression of Compton scattering cross section relative to the Thomson cross section. This also happens when the energy is high, and it's a quantum mechanical effect. And this is how it goes, like the cross section goes like 1 over x, where x is this ratio of energy to rest mass energy, energy of photon before scattering to the rest mass energy of electron. So now this is about when you have electron at rest. So the only thing that can happen is photon loses energy, but you can also have electrons moving fast, like, say thermal distribution of electrons which are very high energy, or power law distribution of relativistic electrons. In that case, in the lab frame, the electrons can have a lot of energy compared to the photons, and they can actually give energy to the photons. And this is sometimes called inverse-Compton scattering, or IC. So here is how do I make it small? So yeah. So here is the situation for inverse-Compton scattering. So you have this lab frame K, in which a photon is incident, photon of energy epsilon, incident, an electron is moving, and this moving electron collides with this photon, and there is an energy exchange. The photon which is coming in at angle theta moves at angle theta 1, and its energy goes from epsilon to epsilon 1. And this is the picture in the electron rest frame K prime. You have electron at rest and the photon coming in at an angle theta prime. So prime is in the lab frame, so it's at an angle theta prime with respect to the x-axis, and it gets scattered. So this is electron rest frame, so the photon will lose energy in this frame because electron is at rest. So you can apply this formula, which was derived by assuming electron at rest. Okay, so here is actually the program that how we should proceed. So you have to start in the lab frame, okay, and then you apply the Doppler formula for the electron, to go to the electron rest frame. So this is how your energy of the photon in the electron rest frame is given by. Now in this frame, you can apply your Compton formula. So right, and here we have assumed this in the electron rest frame. We have assumed that the energy of the photon is much less than MEC squared. So it is almost elastic scattering, because in this frame, the wavelength is smaller, is bigger than the Compton wavelength. This is equivalent to that. So you can just use this formula, and you can assume this to be small, epsilon prime by MEC squared. So you can do this little binomial expansion. Okay. Now, when is this valid? This is valid when, so for most of the photons in this frame, in the electron S frame, epsilon prime is gamma epsilon, right? So if gamma epsilon is greater than MEC squared, then this approximation is valid, right? That is, you can use the Thomson limit. And right, so and if epsilon 1 prime is equal to epsilon prime, that is, 1 stands for after scattering, right? So then epsilon 1 is just obtained by epsilon 1 prime by applying the Doppler boost back to the lab frame, which is just this. So this is the program of how to calculate inverse Compton losses. So we'll actually start from here again. So a few things to notice. So what is the maximum possible energy in inverse Compton scattering in this case, right? So when is this epsilon prime maximum? Epsilon prime is maximum when beta is plus 1 and theta is close to cos theta is close to, sorry, beta is minus 1 and cos theta is plus 1. So basically the maximum value epsilon prime max for all the distributions of thetas is equal to 2 gamma epsilon, right? And if it is still in the Thomson limit, this limit that E epsilon prime is less than MEC squared, in that case we have epsilon 1 prime equals epsilon prime. And now in this case, when is epsilon 1 maximum? This is maximum when this is 1 and this is gamma, right? So you have 2 gamma epsilon 1. So basically, if we plug in epsilon 1, so this should be prime, because we are going back from prime frame to the lab frame. So this should be prime, I'm sorry. So this is prime, so which is equal to 2 gamma times 2 gamma epsilon. So this is equal to 4 gamma squared epsilon. So this is the maximum energy that a photon can attain in inverse Compton scattering. Okay, so this corresponds to actually a head-on collision, right? So so you have a photon and you have a high energy So you have a photon and you have an electron, right? So this is a head-on collision, and in this collision, the photon is sort of gets scattered like this, and this corresponds to this theta, where you have maximum energy, right? But so this is right, but this energy has to be less than gamma MC square, right? Otherwise, this is not consistent with the with the energy conservation in the lab frame, right? The electron cannot give more than its energy through the scattered photon. So this must also be satisfied. So let's see. So you know, MEC square is 0.5 MeV, right? So this is the electron rest mass energy. So even when epsilon prime is say 100 keV, you are in the Thomson limit, right? So this is say 100 keV, which is 0.1 MeV. So if this is 100 keV, and so what would the epsilon be? So epsilon would be like 1 by gamma of that. So you have seed photons. So this will be given by seed photons, which have energy of 100 keV by gamma. So for example, you can have optical photons, and even with like very large gamma of 10 to the 5, you are still in the Thomson regime in the electron rest frame. So this actually assumption is pretty valid, you know, in a lot of cases this is valid. Okay. Any question? No? So this angle theta prime, is the angle between scattered and incident photons as measured in the electron rest frame. And so basically cos, in fact, we are not, you know, theta or theta prime, whatever, is equal to n1 n hat prime dot n hat 1 prime, right? So this prime is in the electron rest frame, and 1 is after scattering, and no subscript is before scattering. So this is the angle. Okay. So this is nothing but, right, so we know that, right, n hat is equal to n hat prime is equal to cos theta prime z hat plus sine theta prime cos phi prime x hat plus sine phi prime y hat, right? So this n hat dot n hat 1 prime will be nothing but cos theta prime cos theta 1 prime. So basically n hat prime is this, and you can just put 1 here, the same expression for 1s. So if you do dot of n hat prime and n hat 1 prime, you get just dot of these things. So plus sine theta prime sine theta 1 prime times cos phi prime minus phi 1 prime. So this is that. So the idea is that this ratio epsilon is to epsilon prime is to epsilon prime 1 is to epsilon 1. Hello?
Yes, sir, we can hear you.
There was a power cut here. I'm sorry about that. Just a second, let me go back to where I was. Hmm. Sure. Hello.
Yes, sir.
Yeah. Sorry about that. Somehow my computer got stuck and I had to restart after that power cut. Anyway, let's try it again. So, yeah. So I was actually telling you about this Compton scattering, specifically this inverse Compton scattering, where photons can gain energy rather than lose energy. The standard case that we are mostly familiar with is in which photons lose energy and the electrons gain energy. But if you go to a frame in which electrons have more energy, more kinetic energy than the photons, then they can actually give energy to photons. So this is what we were considering, right? So this is where we were. So the ratio of these energy is roughly 1 is to gamma is to gamma square, right? Because when you go from lab frame to the electron rest frame, you get a factor of gamma from this Doppler boost formula, and the epsilon prime and epsilon 1 prime are almost the same because of Thomson scattering. You're in the Thomson scattering limit. In the rest frame, the electron rest mass energy is larger than the photon energy. So your electron does not have a lot of energy loss. And then you get this extra factor of gamma from, again, the second Doppler boost to the lab frame. And we sort of mentioned that the maximum energy that you can gain is 4 gamma square. We can also calculate actually the minimum. So maximum energy gain for all possible angles is 4 gamma squared epsilon in the lab frame. But this is only possible if this has to be less than gamma mc squared, right? Right. So 4 gamma squared epsilon has to be less than gamma mc squared. This is just from energy conservation. What about minimum? Right, you can actually see minimum happens when your collisions are not head-on, but tail collisions, right? So there is the Doppler formula. So tail collisions meaning that right. So this was a head-on collision. The tail collision would be in which a photon is moving in this direction and electron is moving in the same direction, and the photon gets reflected. Right. So in this case, the electron is moving away from the photon. So in this case, theta is like pi. So or no, basically what happens is this becomes gamma epsilon 1 minus beta, right? Epsilon prime becomes gamma epsilon 1 minus beta, and that 1 minus beta is 1 by 2 gamma squared. So this becomes epsilon by 2 gamma, and the same way this will bring out 1 over 1 by 2 gamma again. So you have 1 by 4 gamma squared. So minimum energy is epsilon by 4 gamma squared, right? So some photons gain energy, some photons lose energy, and so since it is scattering, number of photons is the same, right? So number of photons is unchanged. in scattering. There is no absorption and emission of photons. It's only changes directions. And so so schematically, if we draw some sort of a spectrum, so if your initial energy in the lab frame is epsilon, right? So the total number, so this is like a delta function or a narrow function. So this is number of photons with energy epsilon as a function of epsilon. With scattering, the area under this curve has to be the same. But what happens is you get something like this. So the area is still the same, but you have, this is broadened because of all these possible values of theta and theta prime and so on. Right, so this spectrum gets broadened and it has a maximum cutoff at gamma squared, 4 gamma squared epsilon, and it has a minimum cutoff at epsilon, let me call this epsilon naught. So epsilon naught by 4 gamma squared, right? And so basically the energy of the photons gets spread, but the mean energy sort of goes like gamma squared epsilon naught. So there is a net gain. So there is a net gain in energy for photons. If epsilon naught is less than gamma mc squared. So this is the inverse Compton scattering. Okay, so there were certain assumptions that we had made. For example, we said that in the electron rest frame, scattering is elastic, that is in the Thomson regime. Okay, so what about, so let's, so what about the total energy? Total energy total energy exchanged or total energy gained by the photons in Compton scattering. So let's do this. This is inverse Compton power for single scattering. So we are considering a situation in which you have photons, you have photons going in all sorts of directions, isotropic distribution of photons, and you have electrons which are also going in all sorts of directions. So right now we are actually considering only single scattering. So how much energy is gained by a photon on scattering with electrons? So let's see. So photon phase space distribution function. So NP, right? So NP is so NP D3P is equal to number of photons per unit volume which has a momentum at P to P plus dP. Right, and we actually have another a related thing which we call V epsilon d epsilon is equal to number of photons per unit volume with energy. So this is all in lab frame. So epsilon to epsilon plus d epsilon. Right. And there is a one-to-one mapping between energy and momentum, E equals PC. So V epsilon d epsilon is equal to NP d3 pip. This is the relation between V and NP. But we know from our previous consideration when we're doing relativistic transformations of various things, we know that D3P transforms as energy, right? So and we know that D3P, D3X, the phase space volume is a Lorentz invariant. So D3P is dpx, dpy, dpz transforms as energy. So if this is the case, then we can sort of divide this and this both sides by epsilon. So this is energy of the photons. D3P by epsilon is a Lorentz invariant, and we know that the numbered in this photon phase space distribution function is Lorentz invariant. Right, so this is a Lorentz invariant. The ratio of these two is a Lorentz invariant. So we know that V epsilon d epsilon by epsilon is equal to V epsilon prime d epsilon prime by epsilon prime. All this is Lorentz invariant. The value of V epsilon d epsilon by epsilon is the same, irrespective of the frame in which you measure it. Now this thing that D3P transforms as energy, you recall when we were doing, right, we were showing that the power, the radiated power is a Lorentz invariant. So we actually dealt with all these things, right? We considered this, right? So we know that dx is equal to 1 by gamma dx prime. This is just Lorentz contraction, and dx dy dz is equal to dy prime dz prime. This is in the transverse direction, and we considered this thing that de dp 0, the zeroth component of the forward momentum is equal to gamma dp0 prime plus right, so beta dp1 prime 1 prime, and we argued that there is no change of momentum. There is no net change of momentum of photons when you go from one frame to other. So that's why dp0, which is like energy, goes like gamma dp0 prime. And we obtained that this transforms as energy. So anyway, the upshot is we will actually need this. So this is somewhat important. So right, similarly dpy dpz was equal to dpy prime dpz prime, because this is in the transverse direction. You're considering boost only in the x direction, and right, and so dpx has to be equal to gamma dpx prime. So this gamma and this 1 by gamma cancel, and so this prime frame is an electron rest frame. So the spread in energy in this case which is dp0 prime, is actually small. So we actually did all this, and we obtained all right. We obtained that d3p, dpx, dpy, dpz goes like gamma times primed things, which is sort of like energy transformation. So this is a Lorentz invariant. So what is the total power? So total scattered power in electron rest frame. This is nothing but dE1 by dt prime. So this is 1 is after scattering, and prime stands for electron rest frame. That is equal to C sigma T epsilon 1 prime V prime right. So this is Thomson scattering cross section. We are assuming we are in the Thomson limit. C is speed of light. This is sort of like a rate per unit volume, or sorry, so this is like a rate times volume, and this is like number of electrons per unit volume times the energy of times energy. So this is, when you multiply all this, you have energy per unit time, rate of energy, so which is power. And so this is in the lab, in the particle rest frame, but we know that if we do epsilon prime here, so so epsilon 1 prime is equal to epsilon what am I saying? So epsilon 1 prime is equal to epsilon prime. So right, so this means that we are in the Thomson limit in electron rest frame. So we can actually just replace it by epsilon prime, and we can put a squared here. Now this is a Lorentz invariant, right? So we can actually write this as this is also power. We know that power is also a Lorentz invariant. So this is actually dE by dt, and this is equal to C sigma T integral epsilon prime squared V epsilon d epsilon by epsilon. Okay, and so basically, so this is equal. This is only true if gamma epsilon is much less than MEC squared, right? Recall this gamma epsilon is like the mean energy, or like a typical energy of electrons in the of photons in the electron rest frame, right? When you do first Doppler shift, Doppler boost, this is what you get. So this formula of Thomson limit is valid only in this case. Now what happens to this one? Right, so what is this? So this is nothing but epsilon prime. So you are going from, so epsilon prime is equal to, so this is the energy, this is energy in electron rest frame, right? So this is just the standard Doppler boost formula, is equal to gamma epsilon 1 minus beta cos theta, right? This is just the Doppler formula for photons going from lab to to test frame, right? So we can actually substitute for here. So dE dt is equal to C sigma t. So we get that gamma squared integral epsilon squared 1 minus beta cos theta squared V epsilon by epsilon d epsilon. Right, so we have this. So now so this is basically the power radiated by scattered electrons. What is this? So we like assume isotropic electron distribution. So dE dt, right? So when you average over all angles theta, angle averaged is equal to C sigma t gamma squared. So 1 minus twice beta cos theta plus beta squared cos squared theta. So this will average times epsilon V epsilon d epsilon. Right, so this is right. So this was number of photons with energy epsilon to d, epsilon to epsilon plus d epsilon. So V epsilon d epsilon is just a number dn times the energy. So this becomes UPH. So this is energy density of photons in lab frame. Oops, lab frame. And what about this? So this goes to 0 because cos theta average is 0. So cos squared theta is 1/3, right? So cos squared theta, angle average cos theta squared theta is equal to 1/3. So this becomes C sigma t gamma squared 1 minus 1 plus beta squared by 3 UPH. So this is your, so if you recall the so there is a very close parallel between synchrotron and inverse Compton. So if you recall, our synchrotron was E dot, so power due to a single electron, P synchrotron due to a single electron was C sigma Tc sigma, okay, sorry, no, sigma Tc gamma squared UB. There was this factor, and there was a 4/3 factor even there, right? It's almost the same formula like this one. You recall this one? When we considered a single electron going around magnetic fields with isotropic distribution of pitch angles, this is what we got. And this was actually just applying this, Larmor formula for the case, in the lab frame when A is perpendicular to velocity and gamma is greater than 1. In fact, even if we don't get gamma greater than 1, this is what the formula is, I think. So I can actually check it. Yes, that's correct. So this is 4/3 sigma Tc beta squared gamma squared UB, and we have this formula here, and we can actually assume, we can assume relativistic. If we assume relativistic electrons, beta is 1. So this is again 4/3 sigma Tc gamma squared u photons for gamma much bigger than 1. Okay, so this is the energy of scattered photons. What about change in photon energy, right? So initially, your original photons also had some energy, so you want to subtract that. So the change in photon energy is is equal to so basically this is equal to dE dt above above minus C sigma T epsilon V epsilon D epsilon. So this is just the same formula applied for non-scattered photons. So if you have non-scattered photons, they just emit so this is just the energy density, and then this is C sigma T. So this is what this is equal to. So this is net power lost by electrons to photons. This is equal to C sigma T UPH. So I'm just going to subtract this from that. So this is gamma squared 1 plus beta squared by 3 minus 1. And this is equal to 4/3 sigma Tc beta squared U pH. There's also gamma squared. So this is this is identical to that, except that UB has become UPH. Now in this formula, so let me just note down this formula. So D, or let me just call it. So just like we had P sync, we'll have P Compton is equal to dE by dt net. Right, so this is sort of negligible, actually, small for gamma greater than 1. This is small compared to the energy density of the scattered photons. So this is equal to 4/3 sigma T C gamma squared beta squared UPH. So this is here, this formula, and this is this formula. Both these formulae are actually valid. These both formula are valid for all betas and gammas, provided but for electrons, for isotropic electron distribution. So yes, so remember, in this formula we assumed that epsilon 1 prime is equal to epsilon prime. That is, you're in the Thomson limit. But if we don't assume that, then this will need a modification, right? So if you're not in the Thomson limit in the electron rest frame, the photons lose energy, right? Some energy. So this becomes right. So this becomes P Compton in that case. is equal to 4/3 sigma T C gamma squared beta UPH, 1 minus 63 by 10 mc squared. This is anyway, you can find this formula in all the books, and so this is gamma epsilon squared by epsilon. So this is the formula, and now this sort of reflects energy loss in electron rest frame. This is energy loss in electron rest frame as not in Thomson limit. By the way, I've actually uploaded some papers in the file section, and this Blumenthal useful papers. This Blumenthal paper, this one, is quite useful. In fact, it gives a lot of details, even more than Rybicki and Lightman, and it actually covers Bremsstrahlung, synchrotron, and inverse-Compton processes. So if you really get if you really want to go in depth into some of these things, this is a good review article which I have uploaded on the course material. I have also put some other useful things. In fact, there was a student who did a project with me on Monte Carlo simulations of Compton scattering, and if someone really wants to get into this is quite he has done actually a Monte Carlo simulation of this scattering process and produced the emitted spectra for various parameters. So you may find this useful. So just check out this class material. Okay, so let me go back to where I was. So basically the upshot is that you can photon can gain energy or lose energy depending on whether they have more energy than the electrons in the lab frame. So here in this formula, this average so this average is not over angle, this is over energy. Anyway, so this is actually given there in Rybicki and Lightman. It's not all that important. For a lot of cases, you can actually ignore this. This is small, right? So this is this is gamma epsilon. So gamma epsilon. So basically, if gamma epsilon is much less than mc squared, this is negligible. You can actually see it, right? This is gamma epsilon. This is mc squared. So basically the energy of the photons in the electron rest frame is small. Then you can ignore this and you have the simpler formula. Okay, so let me create little space. Right, so this is actually extremely important. P synchrotron divided by P Compton is equal to UB by UPH, right? Because they know that all the other factors were the same. So, so if you have same population of electrons, right? So there is magnetic fields, and you have electrons gyrating around these magnetic fields, and there is background photons that can be scattered. So there are background photons, low energy background photons that are isotropic. So then what will happen is, because of this gyration, you will get synchrotron radiation, and because of this upscattering of electrons, upscattering of background photons, you get Compton, inverse Compton scattering. But the ratio of the power in the scattered photons, due to synchrotron emission and due to Compton scattering, is given by this. So if your magnetic energy density is higher than the photon energy density, then your synchrotron power will be more, and otherwise your Compton power will be more. Right. So for example, so you have CMB, right? So you have the cosmic microwave background. So that has some energy density. So the Cmb energy density is, what is Cmb energy density? So the Cmb number density, I know the number density of the Cmb photons. The number density of Cmb photons is about, I think, 400 photons per centimeter cube. It's actually quite high. Okay, I know. So you can actually, for the Cmb energy density is such that if you convert, so b squared by 8 pi, right? So this is the energy density of magnetic fields. So the energy density in Cmb photons is such that b, so b of 3 microgauss, right? If you put 3 microgauss here, that would be the Cmb energy density. So this would be equal to 3 microgauss by b whole square, right? The UB by UPH is this, if you have Cmb background photons. So basically, if your magnetic field strength is greater than 3 microgauss, then the total sorry, B by that, not this. I have it the other way around. Are you getting what I'm trying to do? So I'm just giving you typical numbers. So say, this is B, this is 3 microgauss. So the energy density of Cmb photons is equivalent to having a magnetic field strength of 3 microgauss. So this squared. So if your magnetic field strength is greater than, so if B somewhere is greater than 3 microgauss, synchrotron dominates, right? So this will be greater than 1. And if B is less than 3 microgauss, then inverse Compton now dominates. In terms of the total, this is for total energy losses. So this is actually sometimes quite useful. So for example, so I actually mentioned to you about these galaxy clusters, right? So there are these objects called galaxy clusters, and they have like temperature of about 10 to the 8 Kelvin. So they emit free emission, bremsstrahlung. But the same photons, so same electrons, the same electrons can also inverse Compton upscatter the Cmb. So right, so or another, so this is fine. So these electrons can also upscatter Cmb. These are thermal electrons. So these 10 to the 8 Kelvin is still relativistic, non-relativistic, right? Only for a few times 10 to the 9 Kelvin electrons become relativistic. So this would be, but right, the Cmb energy, the epsilon for Cmb is like, it's microwave. So 1 millimeter, centimeter wavelength basically. So it's actually much less than eV. Whereas whereas the temperature is like you know 10 keV, right? So the Cmb energy is much less than the the Cmb photon energy is much less than the electron's energy. So what it can do is it can clusters can distort the cosmic microwave background by upscattering photons. So this effect has a very characteristic signature, and this is called Sunyaev-Zeldovich effect. And this is actually used to detect, discover clusters at high redshifts, because this is a scattering thing, and it does not depend, the signal does not depend on how far the cluster is. In fact, this is quite, this is a very, very important recent, not so recent, but very, very important diagnostic technique in astronomy. Now, so this is just about free and inverse Compton scattering. But so in these clusters there are also these radio bubbles. So you see synchrotron emission from these radio bubbles, right? So basically this means that there is magnetic fields and relativistic electrons, right? Whenever you see synchrotron emission in radio, it means that there is magnetic field and relativistic electrons. Now the same electrons, for example, these will emit at 1.4 gigahertz, right? And magnetic field is sort of, microgauss, 10 microgauss is the typical value that people throw around for these. But the same electrons can also upscatter the Cmb photons, and so Cmb photons can be upscattered by these relativistic electrons. So here I was talking about the thermal electrons. Here I'm talking about relativistic electrons in these bubbles, which are emitting radio otherwise. So this can actually give you, so here, here, say magnetic field is 10 microgauss. So EB by MC, this is omega cyclotron, is something. If you plug this in, you can get it, but this is actually quite small. Whereas the Cmb photons frequency or lambda is like 1 centimeter. Okay, and frequency of 21 centimeter is 1.4 gigahertz. So this is like 100 okay, so forget about this. So this, the 100 gigahertz is about the Cmb peak, or 200 gigahertz, right? Whereas this is quite small. So what happens is, this, right, that nu equals gamma squared nu naught, right? So this gamma square factor comes from, you go from lab to the rest frame and rest to lab again, you pick up this gamma squared factor. So this 100 gigahertz photon goes to gamma squared 100 gigahertz. Similarly, this guy, so let's just plug in actually, I don't know. I think this is about a few hertz. Typical number is like 10 to the minus 5. So 5 times 10 to the minus 10 is E in ESU. B is 10 to the minus 6, 1 microgauss. 10 to the minus 27 electron mass. 3 times 10 to the 10 is speed of light. So what do we get? Let me just ignore factor of order unity. 10 to the minus 17, 10 to the minus 16. So it's about 10 hertz, right? So the new synchrotron will be gamma squared 10 hertz, not gigahertz, 10 hertz. Whereas this guy is gamma square 100 gigahertz. And if it is like 1 to 10 microgauss, you see the ratio of P sync and P comp is comparable, 3 microgauss is when they are equal. So basically what I'm saying is in these radio bubbles, so you'll have like this synchrotron, this is like the nu to the minus P minus 1 by 2. So this is right. So this would be at, let's say, 1.4 gigahertz. So that's 10 to the 9. This is 10. So gamma is about 10 to the 4, right? If you want to go from 10 hertz to 10 to the 9 hertz, you need gamma of 10 to the 4. Now, if you have gamma 10 to the 4, gamma square is 10 to the 8. So 100 gigahertz Cmb photon becomes 10 to the 10 gigahertz, and giga is 9. So this hertz, which is in gamma rays or hard X-rays. So some of these bubbles are actually, you do see this. This is inverse Compton hard X-rays. So this is, this is say flux versus frequency, right? You see what I'm trying to explain here? So these are this sort of inverse Compton scattering is actually seen for some of these radio emitting plasma bubbles. Okay, so this is fine. So let me so total Compton power for power law electrons. So this was just for a single so total Compton power or power law electrons. So this expression is for a single electron with gamma, but if you have, again, if you have dn d gamma or small n actually, just a sec, d small n d gamma is proportional to gamma to the minus p, or or equal to k gamma to the minus p, right? So if you have a power law distribution of electrons, then how does the total power look like? So P total is equal to 4/3 sigma Tc there is a beta squared here, sorry. Just a sec. Yes, that was the beta squared. Okay, so if we have this power law distribution, all we have to do is just just a second. Let me first write down the general formula and then substitute the specific thing. So this is integral of dn d gamma times power due to a single gamma. So this times d gamma times the volume. So this is power per unit volume, which is like emissivity, right? Because dn by d gamma is number per unit volume per unit gamma. So what do we get here? So this is equal to, or no, it's proportional to or equal to, let's say, equal to k gamma to the minus p times 4/3 sigma t c gamma squared. We take beta to be 1, relativistic particles, and u photon, uph d gamma. So this is nothing but and so there is a power law distribution dn d gamma as a function of gamma. I'm sort of making a log plot. So this is a power law, but you cut it off, you make it go to 0 at gamma min and gamma max. So all you have to do is just gamma to the minus p plus 2. Everything else comes out of the integral, and what we have is 4/3 sigma tc uph, this constant 3 minus p inverse. This is actually extremely simple, right? Gamma max 3 minus p minus gamma min 3 minus p. This is just this integral. Now this is for relativistic particles. We can also, so this is first case. So you can also consider thermal, we can actually consider inverse Compton scattering from thermal non-relativistic electrons. So again, this is the case when electrons are still hot compared to the photons, but their gamma is 1. They have like a Maxwell-Boltzmann thermal distribution. In this case, what we have to do is we have to use this beta squared formula. So you have integral dn dv, for example, p for a given v single electron dv. So we have to do something like so we had this beta squared, so it is 4/3 sigma tc. Gamma is 1 now. You have beta squared, and then you have uph. All this comes out of this integral. Beta squared, right? So e to the and beta squared is nothing but v squared by c squared. So e to the so this is p single. Now we have to write dn dv dv, which is e to the minus mv squared by twice kt, and there is this v squared dv. Right, and there is a normalization. Right, so we need this normalization constant, because this e to the minus nv squared by 2. This is like this, just the Maxwell-Boltzmann distribution. This is not normalized, so we have to divide it by e to the minus mv squared by twice kt v squared dv. Right, so 0 to infinity, 0 to infinity. Right, so we know how to do these integrals. These are these Gaussian integrals. Have you seen these? E to the minus x squared dx, 0 to infinity, and then is equal to square root of pi. In fact, if you have this alpha x squared, this is pi by alpha, and then how do you get, so these are standard integrals. Have you seen such integrals? Hello.
Yes, sir.
Good. Others, if you have this, then you do dd alpha of this, it will pull out x squared, and you can get this v squared and v4 and so on. Anyway, the upshot is this gives you 4 kt by mc squared c sigma t any uph. So this is 4 kt by mc squared times any u photon c sigma t. So this is nothing but some sort of an average value of beta squared, right? This is just average value of v squared by c squared, right? So v squared for a thermal non-relativistic distribution is just kt and divided by c squared. So this had to be of this form. So what this means is that if you have thermal non-relativistic electrons, then this is what your total power is, inverse Compton power is. So so yeah, so in all our emission mechanisms, right, Bremsstrahlung, synchrotron, and even here in inverse Compton, we followed almost a similar procedure, right? We start with a single electron with a given velocity or a given gamma, and we look at the process for that, and then if we have such a population, some distribution of electrons, then we sum over all that. So we are following almost the same procedure here. Okay, so basically, I think I will stop my class. Yes. Hello.
So in the last equation, sir, you have written some any factor out there. I'm not able to get it. Where means what's its dependence?
So this any factor. All right. Just a second. See, this any factor has to be there, right? No, this has to be there. Let's see. So sigma t. So this is dimensionless. Kt by mc square is dimensionless, and c sigma t ne is just 1 over. So 1 over.
Maybe it's under root means integral. It is coming from the integral you're saying.
Yes. Basically I'm actually perhaps this dn dv will have ne, right? This will have some normal. So this is nothing but number of electrons from this velocity to this velocity, right? In fact, this is actually P total by volume again. This is per unit volume. This is like emissivity, because this is number per unit volume, energy per unit volume, and then volume per unit time. So yeah, so I'm just sort of sketching these things out. I'm not deriving these rigorously, but you should actually try to derive these on your own. So in fact, both of these inverse Compton processes, relativistic and non-relativistic, are important. So they are here. The Sunyaev-Zeldovich example, this was thermal non-relativistic. and this was, this inverse Compton due to the synchrotron emitting electrons is non-thermal due to relativistic. So both these limits are actually important. And in fact, this 4 kT by mc squared is quite important. What it means is that this actually represents delta E by E for photons per scattering. And it's sort of it's basically this beta squared factor. Anyway, we'll come to this later. So now now that we have dealt with a single gamma and we have dealt with a simple distribution in gamma, the next step always is to get the spectrum, right? The same thing. We start with total power and then we look at how a single electron what is the spectrum due to a single electron, and then we can consider a population of electrons, and then we look at what the spectrum is. So the procedure is similar, but these microscopic processes are different. Okay. So any other question? See, you have to have the physical picture clearly in your mind, and once you have that, then you can try to follow this mathematics, but the physical picture has to be absolutely clear. And the physical picture is that you start with electron at rest, and that's the standard Compton scattering, and then you say that you can have electrons moving in the lab frame. If they have larger kinetic energy than the photon's energy, then they can actually give energy to the photons. There can be an exchange of energy from electrons to photons, and but the total number of photons will remain the same because it's scattering. There is no absorption and emission involved. And once we have that, then we can actually we have this procedure of going from lab frame to the rest frame, which gets you a factor of gamma. And then this procedure in the electron rest frame, the collision is elastic, and then you come back to the lab frame, which gives you a factor gamma, the additional gamma factor. So you can have actually a gain of gamma squared for the energy of the photon if the electrons have much more energy than the photons. So do please read the book and try to understand. So next time we will move further and try to see what we can say about the spectrum. In fact, there is a very close analogy between the spectrum of the inverse Compton scattered photons and the synchrotron photons. They follow very similar qualitative behavior. So not only this total power formula look very similar, right? Not only this total power formula looks very similar, but even the spectrum is qualitatively very similar. Okay, so we will actually not do the whole rigorous derivation of the inverse Compton spectrum, but I will actually motivate it and then write the final formula. So I suggest you read the book a little bit to get to speed on this topic. Okay. Anything else? Okay, so there is an exam on Saturday for Bremsstrahlung and synchrotron, and yeah, so homework 4 has some problems on that. Okay, so I'll stop recording.
Okay, sir.
Okay, good. Is there any